We're going to begin by just sort of quickly reviewing some of the things we looked at yesterday before we move on. So a reminder, there's three types of velocities that we're going to be considering: constant velocity, average velocity, instantaneous velocity. Constant velocity, of course, means when the velocity remains the same. An average velocity would be over a particular time interval. Quite likely that the speed would be changing, or the velocity would be changing. And instantaneous velocity, of course, is how fast something's traveling at a particular instant, right? And then we did some word problems on constant velocity. And we practiced our conversions, and we practiced our scientific notation. What was next here? Average velocity. We talked about doing it by formula. That's not a very good screen. I got to fix that one. We did some word problems that were ranged from the easy to the a little bit challenging to the, oh yes, now I remember vectors, right? And I pointed out yesterday that, yes, you're going to see vectors for the rest of your high school physics career. So if you thought you were done with them, you are, I'm afraid, sadly mistaken. Okay, I think this is where we left off. Am I correct? Okay, so let's begin here. It says in the example, sorry, I should go back a little bit here, right? So when we're talking about average velocity, you can do it by formula, or in a word problem, or if you have a position time graph like we have here, then how do we find average velocity? And that is by determining the slope of the line joining the 2 points. And the 2 points are the points, the end points of the interval, I guess you could say. So in the example, graph the slope of the line in time, interval A would, in the example graph, comma, that's what I need. The slope of the line in time interval A would yield the average velocity for that time interval. Okay, so how would I find the average velocity then for interval A? Well, I would just find the slope of that line, right? And I haven't given you any points there, but you can see that it looks like it goes up to that point would be the y value there would be 6, right? So that would be 6 minus 0. And here this look appears to be, that's 5, so that must be 1, 2. 2 minus 0. And so the average velocity for interval A is 3 meters per second, correct? Oh, and I think you've got the answer right there, do you? Do I have it there?
Yeah.
No, I don't. That's too bad. Does yours say determine the average velocity for the remaining time intervals? Okay, how about you guys go ahead and do that while I quickly do my attendance. Go ahead and tell me what the average velocity for intervals B, C, D, E, and F are. Notice that F is curved. Okay, I'm hoping nobody spent a lot of time on B, right? Because B is what? 0, right? Flat. C might have been a little trickier. I hope you realize right away that it should be negative slope, right? So way down here, this would be minus 10, right? And up here we're at 6, so it's going to be minus 10, subtract 6 all over. This is a x value here of 10. This is an x value here of 6. Am I right? Yeah. Okay, so but be careful here. Minus 10 minus 6, of course, is minus 16. 10 minus 6 is 4, and that gives you a slope of minus 4 meters per second. Am I right? Minus 4 meters per second? It kind of looks like a 6. I better fix that. Did I make a mistake? That's what you got. D, of course, is 0. We can all see that it's flat. E is going to be, now this point right here, the y value is minus 4. This point here is at minus 10. Now, if I just go like that, am I good? No, because I have to make sure I subtract. So subtract minus 10 over, we got 10, 11, this is 12, this is 13, so that's going to be, just to be complete, let's go 13 minus 12. Minus 4, subtract minus 10. I hope you learned your, double negative stuff, so that's going to be what? 6 over 1, or just plus 6 meters per second. Why is it positive? The slope is up to the right. Correct, right? Up to the right. Now, what about F? Did F cause anybody some grief?
No.
No? What do you have to do?
Same as all.
Yeah, same as all, and you just sort of connect the endpoints. You don't care that it's curved. It's the average velocity. It's the average speed. Okay, so that's going to be here. This is going to be 0, minus a minus 4. Can I just write 0 minus minus 4? Can I just do that in my head? Are we up to that point now, maybe? So it's going to be 4 over 1, 2, 3, 4, 5, or 0.8 meters per second. Yeah? Good? Yeah? All correct? Anyone? Give yourself a pat on the back if you got them all right. Okay, so when determining the average velocity, the following points should be kept in mind. You might want to put a little star beside this. This might be important to you, or you might want to underline certain points. I don't know. Remember that positive slopes rise to the right and they yield positive velocity, and negative slopes drops to the right and yield negative velocity, of course. Positive velocity results from movement in a positive direction, and negative velocity from movement in the negative direction. A straight line portion on a graph indicates a constant velocity. This means that the average and constant velocities are the same value. If average velocity over more than one straight line portion of a graph is desired, then you must construct a straight line from a point on the graph at the beginning of the time interval to a point on the graph at the end of the time interval. If you use the average velocity formula, just make certain that you determine the total displacement over the time interval. That's a lot of words for me to say this. If I wanted to know the average velocity over intervals A and B together, can I just go, well, this one's 3 and this one's 0, average velocity is 1.5. Because, like, there's two of them, average them together. 3 plus 0 is 3, divide by 2, because there's two of them, 1.5. I can do that?
No.
Brandy's, no, she's vigorously shaking her head. She's certain. Why not, Brandy? How about we connect the points and see if we get 1.5? Okay, let's try that. Am I messing with you? Do you feel like I'm messing with you? I'm doing it on purpose. So let's connect the points. What's the y value here? 6. The y value here is 0. What's the x value here? 6. Dot x is, oh, it's just going to be 6 over 6, isn't it? It's equal to 1, the average. She smiles. So which one's right? Is the 1.5 or the 1 right, though, Brent? The 1 is correct. The 1 is correct. You cannot just do that, okay? What if, for example, what if I stayed at this for a long period of time? Like, what if it was 3 for like 2 seconds and then 0 for a really long period of time? Is the average still 1.5? It's kind of like getting 3 out of 3 on one test and 0 on a whole bunch more. Your average ain't 1.5, is it? Okay? You have to connect endpoints. It's kind of like the 0 is weighted more here, because here I've only got 2 seconds of 3 meters per second, but here I've got 1, 2, 3. I got 4 seconds at 0, don't I? So you do not just add them together. You need to connect the endpoints. That's what I'm getting at here in part C. Okay? If average velocity over more than one straight line portion of a graph is desired, then you must construct a straight line from a point on the graph at the beginning to a point on the graph at the end. All right. Last one, a horizontal line indicates 0 slope and therefore 0 velocity. That is, the object is stationary. Okay. Last one, instantaneous velocity. Can be easy, can be hard. There are 2 possible conditions. One, it could be on a straight line graph. In this case, it's easy, because the instantaneous velocity is equal to the average velocity. How come? Because the velocity is constant. The velocity here and there and there and there and there and there and there is all the same, because it's a straight line. The slope does not change. The slope of A, the slope of this interval here in red, is the same as the slope of this interval here in blue, and it's the same as the slope of this interval here in black. They're all the same. So if I'm asking you to find instantaneous velocity on a straight line graph, you just find the slope. You can pick any 2 points you want. Most kids pick the endpoints, but you don't have to. Does that make sense? Am I speaking Chinese? I'm good? I can't speak Chinese. Anytime you're asked for instantaneous velocity in the graph of a straight line, simply find the average velocity for the corresponding interval. By the way, coming up probably about a week from now, I'm going to give you a big chart, how to find everything. It kind of tells like a map how to exactly do what you need to. So you don't need to sort of keep track of all that yet. You need to know it. I mean, you have to learn it as we go, but I'll give you a document that'll help you. Okay, now the last one here that we briefly talked about a little bit, what if it's a curved line graph? And this is really intro to calculus. That's what this really is. Okay, it's probably about day 3 of calculus. They're gonna make it a whole lot harder than it really is. In this case, the portion of the graph over which the b instance is calculated is reduced as shown in the diagram below. As a shorter and shorter time interval is chosen, shown in the diagram of slope C, B, and A, the line becomes progressively shorter, and the curve becomes straighter between those 2 points. So in other words here, slope C from there to there isn't anything like the only point where slope C, let me just make a line here, and I'll do this. Okay, and then I can drag it. So if slope C would be the average for that curvy interval, at what point is it actually equal to the instantaneous velocity? Somewhere about there, right? Only that one instant has the velocity equal to c. Sometime down here, it's actually what? I wanted to rotate that. It's actually steeper here, right? Can I rotate it? No, that's no great. I'm rotating the wrong thing. Up here, it's actually flatter, isn't it? Okay? So, the line becomes progressively shorter. In other words, here we've got a pretty long line between these 2 points. B is shorter. Does the slope of this line, is it closer to the instantaneous velocities on all these points? Yeah. And if I zoom in even more right there, and it's almost so small here, I actually do have to actually zoom in. Let's go into like 200%, right? The slope of A right here, like look at how straight, see the curvy part right there? That curvy part is almost straight, isn't it? Like it's almost exactly the same as the slope of A. In fact, if I went even further, and I can't actually do a whole lot better here, right? But if I took an even shorter period, an interval right there, I mean, the computer can't even make it curvy because the pixels are so big, and it has to draw a straight line. For all intents and purposes, I now have a straight line. And now I just take that straight line and do what to it? Starts with an E and ends in tend. I extend it, okay? I take that little blue line, which is basically that curve, and I just stretch it out, and then I pick 2 points. Most kids pick the end, and I find the slope of those 2 points. And what's that line that I just drew called? Tangent line. Okay, that's called a tangent line. Seriously, they spend about an hour and a half explaining that in calculus class. You can snooze through it if you want. Yeah. Okay, so since decreasing the length of the time interval caused the portion of the graph to be straighter, it would be reasonable to assume that a very short piece of graph would, for all purposes, be considered a straight line. It would be impossible to find the slope of such a short line, but we can employ a construction method which will lengthen and consequently allow us to calculate the slope of the line under consideration. The construction involves drawing a tangent line to the point where we want to find the inst on the graph. This tangent line represents an extension of the very short piece of curve, I should say, not line, that was mentioned earlier. The construction of the tangent line is shown below. It's actually up here. Oh, I guess it is there as well. Okay, so draw the tangent line that best approximates the slope of the curved line at that point, and let's go find the slope. Now, what do you guys have? You have it drawn, right? But we need to actually, we don't have any numbers on there, do we?
No.
Can we make up numbers? Let's make up numbers.
3, 4, 5, 6.
Let's just go like this. Oops. That's kind of silly of me. Let's go, yeah, 1, 2, 3, 4, 5, 6, 7, 8, and minus 1, minus 2, minus 3, 4, 5, 6, 7, 8. Minus 8 down there. Right. Hello, Mrs. Jaddy. You don't have to pick the endpoints, okay? Now, does anybody know what the actual grid points are called? I used the term there called a grid point, but there's actually a special mathematical term for them. Probably, I'm guessing nobody but me, probably in the whole province knows it, maybe. I don't know. It's not very common, anyways. I guess that's what I'm trying to say. They're called lattice points. You know the lattice you put in your garden, right? It has that sort of diagonal, kind of diamond shape, that kind of stuff. So these are actually called lattice points, where the grid points actually meet. So find one that's real close to a lattice point. That one right there I'm going to call 7, 0. And now can we find another one? Right here, maybe? I'm going to go with this one right here. So that one's going to be 1 minus 7, I think. Yeah, I need to redo that little picture there, right? So now we're going to find the slope. So the rise over the run is going to be, it's going up 7, right? 0 minus 7. Subtract my x's. 7 minus 1, so that's going to be 7 over 6, or 1.18, am I right? What's 7 divided by 6? How much? 1.16? What did I say? That was close. Okay, so yeah, tangent lines may sound hard, but they're not. The only real crucial thing is are Jordan and Jason going to get exactly the same value? They might, because they're sitting side by side, right? But Jordan and Jake might get different ones because they're not really sort of looking at each other. Is this about right? Right? So, I mean, Jake might get like 1.4 and Jordan might get 1.16. Is that okay? Absolutely. Their tangent line, I mean, who's to say whether your tangent line is better than his? Right? As long as I see an actual tangent line and I see a slope calculation, you're going to get it. Okay? As long as it's sort of, within reason. Good? Yeah? Okay. This always challenges kids. I really need to come up with a better graph here. But for the time being, I would like you to find instantaneous velocities at points A, B, and C. Now, you might need a ruler. You can use a straight edge. It doesn't have to be a ruler that measures. All it has to be is something that's straight. Okay? You need to find tangent lines at A, B, and C. All right, let's check these here. Now, I'm going to have a hard time because for me to draw a tangent line on here is pretty tricky. I have to sort of draw the line and then drag it. And so bear with me a little bit here. All right, so from A there, now, again, see, that's not quite right. I need to... How's that? Okay, and again, your line's going to be different than mine. As long as you show that you know the process, I'm good. Okay, I got to find the lattice point here. There really isn't one there. So what do? You actually extend it if you have to. Okay, you can go as far as you want until you find a good point. I would say that's a good one right there. And I don't know, do they have to be one on either side of the point, or can I pick those two? I can pick any two I want. It's the straight lines. Okay? So I'm going to get a slope here now. This is going to be 19 minus 10 over 20 minus 12. So that's going to be 9 over 8, or that's going to be 1.125. Is that what someone got? If you got somewhere between, like, what do you think the range is that I would accept?
I got 1.
1? Would 1 be too low, or is that within the reason, do you think? I mean, all this has to be is out by 1, right? 9 over 9 is 1. I think 1's certainly within reason. I would probably go all the way down to minus 9, or 0.9, I mean. 0.9 to about 1.3 would be fine. Okay? As long as you show me the tangent line, it helps if you circle the points, and then I can understand what you're trying to do, what you're trying to show me here. Okay? Now B. What the heck do we do with B? Because it's almost straight there, right? Now here's where I kind of get some issues sometimes, because kids say, well, Mr. Bennett can only touch it at one point. Well, that's true, but that's assuming that the curve remains the same, right? Like here, B, what you're really doing, get that out of your head that it has to be only touching at one point. It's really just a line that estimates the curvature of the curve at that point, okay? And then don't worry about the rest. So, does that estimate the curvature right there? Yeah, I think that's pretty close. Don't worry that, how come it touches again down here? Well, because the curve changes, right? It's going off, it's kind of curving back a little bit. So of course it's going to touch, right? So go ahead and pick your 2 points there. Okay, do I need to go through each one here? Do you think? Probably not. What do you guys get for an answer there? Like it's going to be a little bit more than 1.1. So around 2? Okay, so something around 2 is fine, right? Way down here at C is going to be, well, it's going to be negative, right? Looks to be about a little less than 2. I'm going to guess about minus 1.8. Did I guess good? 1.5? Yeah, anything in that minus 1 point something area is perfectly fine. Good, Zach? Yeah? Kaylin, good? Yeah? Evan, good? Yeah? Okay. Alrighty, so I'm going to give you some time to work now. There's actually 4 graphs at the end. I would like you to, and I know you got all weekend, you got about 20 minutes left here. I'm going to be a real jerk and I'm going to say do all 4. But you do have a fair bit of time. Okay? So go ahead and do all 4. Answers are on the back.
Do you want to step up?
You can check them as you go. I will find a TED Talk and I'll fire it up about 2:10. Okay? You should be able to get the first couple done right today, I would think.